So as I discussed in my last video, today we are going to discuss, in this video we are going to discuss two very important topic. One of them is global stability, when we can say that it is globally stable. And the second one will be a very powerful tool where we will, instead of investigating stability, we will investigate instability, right? So now global stability, let me just show you something. uh, Again, we started with the same system, same autonomous system. As of now, we just confine our discussion to autonomous system. We are not discussing or not considering anything about non-autonomous or forced or anything. We are considering we can say a very special class of system that is autonomous in nature, that is shift invariant. So, and also we are assuming that x is equal to 0 is the equilibrium point. Alright, now we are defining a function in similar way. This be a continuously differentiable function such that so if we observe that norm x tends to infinity implies Vx tends to infinity, like in means if I have to express it in word, then I say it is a case that is Vx is radially unbounded function. So here you will get that v dot x is equal to 0, sorry, less than 0, if v dot x less than 0 for all x not is equal to 0. See here in the previous case, what we used to define for all x belongs to d minus 0, but now we are actually getting Vx defined over, instead of capital D, now it is defined over your entire state space. So if it is defined over entire state space, then that notion of D, actually here in this case D becomes your Rn. So that is why no need to mention it, rather we can say it in a simple way that for all x that is sorry, no, for all x that is not is equal to 0. It is a simple way to state this. Now here that then we can claim that the system defined by equation x dot is equal to f of x is having asymptotically stable equilibrium globally asymptotically stable equilibrium at. Now this is very important to note what observation or inference you can draw. Like, for if we consider the pendulum example, can we have a global asymptotic equilibrium point? The answer is obviously no. Any nonlinear system that contains more than one equilibrium point cannot offer you global asymptotic stability whatever you do, until unless you completely change its dynamics and make sure that only one equilibrium point exists. You cannot claim or cannot, no theorem, nothing required. It's simple common sense that if there exists another equilibrium point, then whether that is stable, unstable, whatever, obviously even if you have two stable equilibrium point, still also what you will have your means state trajectory when it will be in vicinity of, say, let us consider one equilibrium is equilibrium 1, another one is equilibrium 2. When your state trajectory within the domain of attraction of equilibrium 1, they will run towards equilibrium 1. When it will fall under domain of attraction of equilibrium 2, then they will run towards equilibrium 2. Now even if there is some overlapping zone, then it will be like they will means be drawn towards the equilibrium point having that more stronger stability property. Now anyway, whatever you can have, it's very clear, very clear that if you have multiple equilibrium points, no way you can say it is global. The way or idea of a global means the notion of global equilibrium point means from anywhere on your state plane you can means your initial condition can be anywhere, but from that your means trajectory will be drawn towards your means equilibrium point. So that is the notion of global equilibrium means asymptotic stability. Now see what we can have now. So now let us try to prove it. Like let us consider any point, given any point let's say is equal to Vp, and for which we can have this condition means radial unboundedness is satisfied. So what will that this condition implies that for any c greater than 0 there exists r greater than 0 such that Vx greater than c, right? Whenever norm x is greater than r. So how we define it? Let c is equal to Vp, where suppose p is at a distance r, there exists r greater than 0 such that Vxc whenever norm x is greater than r. Now thus we can have, like previous argument, we can have a region omega c that belongs to the ball BR, where it implies that omega c is bounded. Now, if omega c is bounded, actually what you need to do here is that you have to, like, I am not again try to means I have to write again then everything which I don't want here. Like here, yes, if you see that we can, means continuously we can have bigger omega c, like here we have omega beta, now we can have bigger omega c, and for that we have bigger br, and actually we can finally realize that omega c will become very large and br will become infinite, and means there is no such, means it is like an iterative process, and you just by method of induction you can prove on for bigger omega c, bigger omega c, bigger omega c, and eventually you will reach to a conclusion that it is a global asymptotically stable system. So that's all. Now what is there that like, now we'll go to a powerful theorem that is due for instability. So like instability is very important to us. Now while dealing instability, we will deal with this. This is known as Cheatev's theorem, or Cheatev's instability theorem. Now, before we start this, let us introduce, or let us get to know some terminology. Like, again, we will define be a continuous, just let me check whether it's recording, be a continuous continuously differentiable function on a this 0 means the origin belongs to D, or you can say that in this way also you can write. Now suppose we have V of 0 is equal to 0, and there is a point x naught that is arbitrarily close to the origin, such that then we can choose r greater than 0 every time I am facing an apprehension, or means feeling apprehensive that I have reached the end of the page, so that I won't get any means further space to write on the same page. Anyway, so choose r greater than 0 such that the ball br, all these are not, means most of the cases you will find these are closed ball. Why it is closed ball? I am claiming that it is x. Had I considered only this, then it would have become an open ball. Now it is contained in D, and let capital U is equal to x belongs to BR such that so basically what this U set will contain, U set will contain all the x point inside a ball BR for which you will have Vx greater than 0. Now that the set U is a like we can say that U will be a non-empty set. How am I so confident to claim that U is going to be a non-empty set? Because if you know that by virtue of its definition, Vx can only be 0 at origin. All other point Vx is obliged to greater than 0. Now we have defined Br for like a ball where like r greater than 0. So it is, even if r is very small, or means this Br is of a diminishing radius ball, or means a ball that is continuously shrinking volume wise towards the origin, but still it will have some volume, and obviously some points will be there, right? And those points, obviously, as those points are not at origin, all those points you will have Vx greater than 0. Then we can have this. Now, so we can say that the set U is non-empty, and of course it is contained in BR. Now its boundary is the surface Vx is equal to 0, and that surface is like a sphere. What is a sphere? Sphere is nothing, just if you take a ball and if you take only the means, what you mean by I do not know how many of you have played during your young age with normal rubber ball. That normal rubber ball is just like having a very thin skin and means inside it's completely hollow. Or means you can even consider a means football that is properly pumped and means enough air is there. There is no such kind of means that the surface of the ball is very smooth and even and means quite like the ball is giving you the outward of the ball is giving you completely shape of a solid means solid 3D sphere. Then if you take the outer skin, they again form a ball like a hollow sphere. Then that hollow sphere we meant that it is the sphere in our mathematics. Like the three-dimensional means a hollow object with just having a skin at its surface. So this and the sphere, this one is like we are having with is equal to 0, the origin lies this very strange thing, you will figure it out. Of u inside BR. Okay, one thing here, what we know, like if we just completely means not completely, if we just somewhat manipulate that definition, like previously v was strictly positive outside, like if we just replace that positive definite v by a positive semi-definite one, and even if we replace positive semi-definite v, then also we can have a few points outside your ball where you will have this condition. What I am trying to say, let me just reiterate once again that this first part is clear to you. Now we are choosing r greater than 0 such that we are getting this. Now we are defining this, try to understand this definition. Actually I also got disconnected due to some people are continuously texting me on WhatsApp. Anyways, so u is equal to mod x belongs to BR such that Vx greater than 0. So now if we replace the V, the positive definite one, by like positive semi-definite or means sign indefinite function also, then we can have a certain zone where Vx 0, where Vx not. I think one example will help you. So what example we can take here, like we can take an example of is equal to say many example you can have. One is half x1 square minus x2 square. So you will have u like this. Yeah. So now you have this one, this radius r we know, and we are having and similarly this side. This 2 is my u. So here you are getting x belongs to BR. Huh? BR is the ball. This is BR, that radius, and this one is inside this. We are getting u. Now another Vx we can have like. How it would look like. Then this will become u. This is again BR, right? Now, with this, we are going to define the Cheatev's instability theorem. So, what is that Cheatev's instability theorem? Let me write. Cheatev instability theorem says that let actually I am taking an antibiotic course, so feeling very drowsy and very tired, but can't take break because of your semester and means days means are very means few days are left in our hand. So let x for x dot is equal to f of x. Let us define v d to r. Now here see the definition. Likely I think I have made a slightest mistake there. Yeah. Now we can remove this one. Like only thing that is required is that v d to r be a continuously differentiable function. Like previously it was a strict requirement on V that it has to be positive definite. But now try to understand this, please note it, like it is only continuously differentiable function no need to be so now we have such that we are having V0 is equal to 0 and Vx naught is equal to 0. Sorry. Vx naught greater than 0 for some x naught in now we define a set U. How to define U? Like U is contains X belongs to a ball BR such that Vx greater than 0. So if that is the case, then in addition if we find if let us remove the first person sentence from our narration. If V dot x greater than 0 in this capital U, then x is equal to 0 is an unstable equilibrium. Right. So now let us try to prove this theorem. Before proving, let me once again quickly recap that what was the statement, because in between I have to receive a lot of calls and I got distracted. So let me just quickly recap. So here what we are doing that autonomous system remain autonomous, origin remain our equilibrium. V, the definition of V has slightly changed from continuously differentiable positive definite function to a continuously differentiable function where the sign definiteness has not yet been mentioned here. Like I have written here also, no need to be sign definite on the entire domain. However, v naught is equal to 0 and we are assuming an arbitrarily close x naught to origin for which vx naught greater than 0, and then we are defining a set u in such a manner that set u contains all x belongs to Br such that for them Vx greater than 0. In addition, if we find that V dot x is greater than 0 in that same u, then x is equal to 0 is an unstable equilibrium. It's clear, very clear. And means intuitively we can also understand, because in u your Vx is greater than 0, means your Vx is some positive number. See, this Lyapunov, it's actually basic and your just application of common sense is sufficient. Lyapunov has formulated it in such a way. Like if you see that Lyapunov, what he says that if Vx greater than 0 and V dot x is greater than 0, then obviously means like you are having a positive number and its rate of change is positive. So gradually it will increase. Now, if you have, on the other hand, a positive number with negative rate of change, gradually it will reduce to 0. Now, if somehow, if you can ensure that function is lower bounded, then it will give, will stop at 0. That is the case in case of asymptotic stability. Now, see how to prove this instability theorem. Now, instability theorem, we can prove it like here, the point x naught is in the interior. Now obviously you will ask me what is interior, and I do not know how many of you will actually notice that there is a term interior and how it is different from interior designing, but it is my duty to make you aware of this interior point, what is meant by interior. So now here with removal of that restriction, we are having this and we define u. Now the point x naught is in the interior of, let me discuss what is interior. Now this interior of, again phone call. Now see here, instead of giving you a topological definition, I think you will be able to understand a simple definition. Let us consider a region here, a irregular region I am drawing in x1, x2 plane. So this is x1, this is our x2. In this region, if you pick up any point, just not on the this curve, whatever be this curve, which one is responsible for separation of this entire plane in two regions. One is inside this curve and another one is outside this curve. So if you take any point arbitrarily close to its boundary, or maybe far away from the boundary, almost at the center here, but not on the boundary, then for all these points, actually I could not discuss the concept of Hausdorff space. Had I got had I discussed it, notion of Hausdorff space, you will find it quite easy to understand. But anyway, you can, even if without that discussion, you can visualize it. Like, let me help you. See here what I am trying to say. It's a very simple thing, that even if you are taking a point that is very close to your boundary, but around that point you can always figure out. I think this color is not quite clear. Say you are taking this point, so around this point you can figure out a neighborhood that with a very small eta, and means now it may appear to you like as if we have means this neighborhood collided with the boundary, but we can zoom it and we can see that it's not like that. What you are thinking about, it's not the actual case. See, yeah, just a minute. See, now see, it is not touching. If you zoom it further, then you will see that it is not touching. And like for this green dot, like you can have means any other point that is much closer to your boundary, and you can figure out a neighborhood around that point. But even still that will not means close to your like if you draw this, if you again allow it to shrink means or means retain its normal size, it will appear to you as if you have collided with the boundary, but actually you will not until unless you take a point that is exactly on the boundary. You will always find some point like now if I write a point that is not in boundary but very close to boundary, you think, oh, then sir has means for this no neighborhood means can be drawn. Now let me show you. If I do this, then what was that point? Yeah, this one. So this is the point. Now for this, I can still draw my neighborhood like this. Yes, means I cannot draw very means actually a circle, but means you can draw a circle with smaller radius, and then if you again return back to your normal size, you will see that uh, yeah, as if you have collided with the boundary, but you have not. Actually, that point what I drawn it was here. Now you cannot spot it even. So what is that? Is the what I just want to show you that what is boundary and what is that interior. So every point that is not on the boundary of a closed curve, rather it means however close to boundary but means not on the boundary of a closed region, then that is an interior of a point. Now what we are trying to say, from where all this started, all this discussion and all these things come in picture, like just let me check whether it's recording. So that interior, you got certain idea about the interior point. Now what you can do here is that the point we have the point x naught is in interior of u, and Vx naught is equal to a greater than 0. So the trajectory whatever you have, the trajectory xt having or xt starting at uh, now to see or to verify this, we need to notice that as long as this xt is within u, what you will have that your vxt is like upper bounded by a, right? Because as v dot x greater than 0 in our this region u, so what we can write, we can figure out y means gamma is equal to minimum value of v dot x such that x belongs to u and Vx greater than is equal to A, right? So this gives us the now minimum of such V dot x will be picked up and that will be gamma. So what we will get here by picking up such a gamma, that and obviously if you have a doubt regarding existence of such minimum, we can show you that gamma will always exist because v dot hat x is a continuous function over this u, and if you have noticed by construction, u is like compact set. Compact set, what is the notion of compact set? Closed and bounded. So how we have defined u? See, u contains all the x within a ball of radius r. Obviously that means you are confining such that Vx greater than 0. So Vx greater than 0, so it is obviously it is closed and bounded. So if it is closed and bounded, then what we will get, gamma is equal to minimum value of this, means this minimum value can exist. Like if this set is not compact, then there is no guarantee that you can find out a minimum point within that range. Had we considered open or unbounded set, it is difficult for us to tell that minimum value. But when we are talking about closed and bounded set, obviously we can figure out minimum and maximum value of continuously differentiable means continuous function, right? So if this v dot x is continuous, then we can figure out the gamma, and if this gamma should be greater than 0 because v dot x greater than 0. So what we can write is like Vxt is equal to Vx naught plus T0 V dot x tau d tau So that should be is equal to what? That should be greater than a, because this first part will give us a plus like this is the minimum value of Vt. We are finding the lower bound for Vt, right? But even if it is the lower bound, like Vt will always be greater than or is equal to this. So at its minimum value, Vt is v of not Vt, rather v of x is equal to this. But still, you can see that it contains means linearly means monotonically increasing time component. Time can only progress in a means positive direction. So if I go on increasing time, it will go out of bound. So obviously it will leave the closed set, because U is a closed set, U is a bounded set. So this cannot stay forever in U. So means it will leave. Now x this xt can't leave. This is all another means technique, not technique, rather cannot leave like through the surface on which you are having since we are obliged to maintain right. So what it will do, it will leave that you will live through the sphere means it will if I have to represent it in diagram, then it will be this cannot move in this direction. Why? Because vxt has to be a, and if you notice, then everywhere for this function on all this line, this one is x1 is equal to x2, and this line is x1 is equal to minus x2. So on all this line you cannot have this, right? Means all on these lines, on these two lines, your v is 0 along these lines. So these if your trajectory start here, then it cannot go in this way. So what it can do, it can move in an outward direction, right? Without means like without making a collision with your boundary where Vx is 0. But as it leaves the ball, obviously your system is an unstable one, right? So let us take a small example. I hope that will further clarify our means clear our understanding on that set one. Where G1 dot and G2 dot are locally Lipschitz. So, and they also satisfy the following inequality, these two functions are bounded by your Euclidean norm, right? That is in a neighborhood D of the origin. Now, if this what neighborhood evoke your an idea of vanishingly small region, that is not the case. Neighborhood can be anything, right? So that neighborhood, then what we can write, from that, if we take this Vx is equal to half of that same one, and then you can see that the diagram, let me just copy that diagram here. This one. So what we are trying to do, we are trying to copy. So So what you will see here, it's very interesting that on this line, x2 is equal to 0, your Vx is positive, right? So on line x2 is equal to 0, your Vx greater than 0. So let us take any point that is arbitrarily close to origin. Here, say one point. Now we can set u in this way, and the derivative of Vx along system trajectory will be what? Will be x1 square plus x2 square minus it will be plus x1 g1 x minus x2 g2 x, right? Now the magnitude of these, if they satisfy what again we have reached here. Now see, I don't want to change the page, rather I would like to explain it here only, that you are means considering a region where x2 is 0 or very close to 0. So on that you will have this, if you take some point on this line itself, not on the origin but very close to origin and on the line where x2 is equal to 0. So this part, this second term will means not be present due to this greater than 0 term. Now you can see that you are having v dot x like it is will become this inequality. So now what we can write here, that v dot x becomes greater than is equal to just a slightest manipulation yield this. So that will result us so if you select R, what is R? That determines the radius of this ball. So if you select R, that is 1 upon 2k, then what would happen? This will boils down to a positive number. So you will get the origin itself is unstable. For R is equal to 1 by 2k, or R that is less than 1 by 2k, your origin will become unstable. So this is all about Cheatev's instability theorem. Now in the next section we will study invariance principle, and gradually we will move to the converse theorem, that is the most generalized form of Lyapunov application.